Now that we've seen what local extrema look like, we should also talk about how to find them because these are very important points for our functions. The way we're going to find them is we're going to use this thing called the first derivative test. So let's let c be a critical number of a function f. And remember, for c to be a critical number, we need a couple things. We need f of c to be defined. So in other words, c must be in the domain of f. And either f prime of c is equal to 0, so the derivative is equal to 0 at x equals c, or f prime of x does not exist. Then when we construct our sign chart, we're going to see one of four possibilities. So here at c, I don't necessarily know the behavior here, but I know that the derivative is either 0 or does not exist. It's going to be one of those two things. Let's say that our function is, our derivative is positive on the left-hand side of c and negative on the right-hand side of c. So what does that mean? If our derivative is positive on the left-hand side, it means we have an increasing function on the left-hand side, and on the right-hand side, our derivative is negative. That means our function is decreasing. So let's draw this out for a second. We have a function which is increasing, and then at c it stops, and then after that it's decreasing. Well, look at this right here. That looks like a local maximum to me. So in other words, if I have this situation, if I see this on my sign chart, that means that f of c is a local maximum. We could also state x equals, let's say this. Let's say we have a local maximum at x equals c. So I want to draw the distinction between these two statements because they're sort of saying the same thing, but in slightly different ways, and the wording does matter. Whenever we talk about what the local maximum is, we always want to talk about the y value, which is why we're talking about f of c. So we would say, okay, the local maximum is, and then you would give the y value of the function at x equals c. But when we talk about where these local extrema occur, we always refer to them as x values because that tells us where exactly our function achieves that local maximum. So if you want to say the local maximum is this, we're talking about a y value. But if you want to talk about where that local maximum is, you're talking about its x value. So let's suppose then that we have the opposite case. So let's suppose on the left-hand side of c, my derivative is negative, and on the right-hand side of c, my derivative is positive. So that means my function is decreasing on the left-hand side and increasing on the right-hand side. Again, draw that out. I would have a function that maybe looks something like this. And then I see right here at this point, well, that looks an awful lot like a local minimum. So in this case, we would say that f of c is a local minimum, or we have a local min at x equals c. So we're mostly paying attention to what does our sign chart look like. And I think that drawing these arrows in helps tremendously in identifying whether you have a local minimum or a local maximum. But we have two other possibilities that we haven't really discussed. We could have something that looks like this. So let's say at c, let's say our derivative is positive on the left-hand side, which means our function is increasing. And let's say it's positive on the right-hand side, it's increasing again. So our function is positive. Let's say we have a horizontal tangent line at c, and then after that it continues to be positive. What's going on right here? It looks kind of like it's an important point. It does feel like it's an important point, but if I'm thinking about this just in terms of local extrema, it's not a local maximum. It's not a local minimum. So what that means is that f of c is not a local extrema. Extremum would be the singular. And then similarly, if we are decreasing on both sides of c, so let's say here at c, our function is, or excuse me, our derivative is negative on both sides. That means our function is decreasing. Again, draw out that picture. It looks something like this. This point right here feels important. It looks like something important must be happening there, but it's not a local extreme value. So that means that, again, f of c is not a local extreme value. So mostly what we're looking for is when we perform this first derivative test, when we construct our number line, which is something that we are already doing, by the way, we're mostly paying attention for, do we have a sign change in our derivative? Are we changing from positive to negative, and are we changing from negative to positive? Because those are the really interesting cases where we either have a local maximum or a local minimum. If we don't have a sign change, then it's not a local extremum. There might be something else interesting happening at that point, but it's not a local minimum, it's not a local maximum. So we're going to look at a few examples here. First up, I have f of x equals negative x cubed plus 12x plus 8. We would like to find the intervals where f of x is increasing, the intervals where f of x is decreasing. So first of all, we've done this before. The new part is and the local extrema. Most of this problem should feel pretty much the same. Really, it's just going to be a couple of added extra steps at the end where we're just looking to identify, do we have any local extrema? So I need to start by finding my critical numbers, which means I need my derivative. So f prime of x is equal to negative 3x squared plus 12. And remember, for critical numbers, I want to take my derivative, f prime of x, set it equal to 0. Here, negative 3x squared plus 12 equals 0. We can solve this pretty quickly. I should get 12 equals 3x squared. So x squared equals 4. Remember, here we're going to end up with x equals plus or minus 2. And remember that the critical points must be in the domain of your function. So here, we're working with a polynomial. The domain is all real numbers, which means that negative 2, positive 2, these are critical numbers. Again, the other thing I want you to just get in the habit of checking is places where your derivative does not exist. Here, f is a polynomial. And I'm just going to make a note there that f is a polynomial. So we don't have any solutions. Sometimes I'll even write, hey, there's no solutions to that particular case. But I want you to, again, maintain that habit of thinking about it just so that we don't forget to when we actually do have a critical number there. So these are only two critical numbers, negative 2 and positive 2. I found my critical numbers. Let's go ahead and construct our number line. So I'm going to construct f prime. We have two critical numbers. We have negative 2 and positive 2. And I also just want to make a note here that, hey, the derivative was 0 at each of those. So I'm going to put a little 0 above each of those so that I know exactly what's going on there. Remember, if the derivative is 0, I have that horizontal tangent line. All right, so now I need to figure out what's going on in each section of this, within each interval. So I'm going to pick a number in each one of these intervals and plug those into my derivative. Let's see if we end up with a positive answer or a negative answer. So let's start with, how about negative 3? That's going to be over here on the left-hand side of negative 2. I have negative 3 times negative 3 squared plus 12. Careful with your order of operations here. This is negative 3 times negative 3 squared. That's a positive 9 plus 12. So I have negative 27 plus 12 gives me negative 15. So my derivative is negative over here, which means that my function is decreasing. So okay, that's very cool. Now I need a number between negative 2 and positive 2. 0 seems like it would be a very good choice here, so I'm going to take 0 and plug that into my derivative. Negative 3 times 0 squared plus 12. We've got 0 plus 12 gives me 12. So my derivative is a positive 12 between negative 2 and positive 2, which means that my function is increasing over that particular interval. Now I need a number on the right-hand side of positive 2. I think 3 would probably be the easiest choice. Let's do that right here. F of 3. This is equal to negative 3 times positive 3 squared plus 12. Negative 3 times 9 plus 12 gives me negative 27 plus 12. Hey, look at that. I've got a negative 15 here. So my derivative is negative, which means my function is decreasing. So all of this work, nothing we've done so far really is a whole lot different than what we've done in the previous examples. And even the first part of our answer, when we kind of look at what we've got right here, we're just going to say, okay, well, our function is increasing. Actually, let's just give that over here. Our function is increasing on negative 2 to positive 2 right here in this section where our derivative is positive. And our function is decreasing on negative infinity to negative 2, negative infinity to negative 2, and positive 2 to positive infinity, 2 to positive infinity. So that part we already knew how to do. The new part of this is now going to come from, let's find our local extreme values. So I'm going to look at my number line here. I'm going to look at this number line and say, okay, what's happening at negative 2? Is the sign changing? Well, yeah, it's changing. It's going from decreasing to increasing. If you need to, draw yourself a little picture right there. What's going on? That looks like a local minimum. So I've identified that this is a local minimum at negative 2. When we give the local extrema, I don't recall what my math lab is going to look for, whether it's looking for an x value or a y value, but it's safe to have both anyway. So what I'm going to do is I'm going to take negative 2, I'm going to plug that back into my original f of x because that's what tells me the y value. I'm going to plug that back into my original f of x, and then that will give me the y value. So f of negative 2, this is opposite negative 2 to the third power, plus 12 times negative 2, plus 8. So I have negative, let's see, this will be negative 8 minus 24 plus 8. So here I have 8 minus 24 plus 8. 8 plus 8, 16, and minus 24, I have negative 8. So we have a local minimum at, we can give our answer two ways. I believe the way my math lab does it, they'll say f of negative 2 is equal to negative 8. But if you gave me an ordered pair, negative 2 comma negative 8, that's a lot of times that's how I'll write my local minimum. So there we've got that. And actually, I'm kind of running out of room, so let's erase this right here. Well, what's going on then at positive 2? Our function is increasing and then decreasing. What's going on right here? Looks like we've got a local maximum. So I'm going to take positive 2 just like I did with negative 2, and I'm going to plug that into my original function f of x. So f of positive 2, I'll have opposite 2 to the third. And actually, let me give myself a little bit more room. I think I'm going to run out there. I have opposite 2 to the third plus 12 times 2 plus 8. So I've got negative 8 plus 24 plus 8. Here I should end up with a positive 24. So when I talk about what's going on here, I can say that, well, I've got a local maximum at f of positive 2 equals positive 24. Or again, if you wanted to give the ordered pair 2 comma 24, I think that's perfectly fine as well. So this is pretty much everything the problem asked me for. It said, okay, go find where it's increasing and decreasing. We've done that. And then find the local extrema. We said we have a local minimum at f of -2 equals -8. And we've got a local maximum of f of 2 equals 24. This is everything the problem asked me to do. But I want to do just a little bit more here. I think, boy, because I'm just about out of room here. Boy, I sure am. I want to just make a rough sketch of this graph because we're going to be doing a lot of graphing, and I think the earlier we start practicing, the better. So I'm going to erase this section right here. When I construct my graph, I'm going to look at, let's see, I'm going to look at these points that I found, these local extreme values. So let's see, I have a point at -2, let's say 2, 4, 6, 8. I've got a point right here at -2, -8. And 1, 2, let's say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Another point way up here. And I always like to draw in what's going on exactly at those values, and then we can sort of fill in the blanks later. We said that the value of the derivative was 0 at x equals -2 and x equals +2, which means I have that horizontal tangent line, and I sort of drew those in already right here with that, and then, oops, let me try and just get that, there we go, that and this part right here. So I'm going to sort of mimic that here on my graph right at those points. Here I've got my local maximum, and again, just maybe double check, hey, we've got this local maximum at 2, 24. And then at -2, -8, I've got this local minimum. It's going to look something like this because we have a horizontal tangent line. And then again, I think after that we can sort of fill in the blanks. If you need to, refer to this part where your function is increasing or decreasing, or look at your sign chart right here. They both kind of tell you the same information, it's just different ways of presenting it. Our function is decreasing on the left-hand side of -2. And then after that it switches, now it's increasing. Once we hit that maximum, then it's decreasing once again. Our function is going to look something like this. So this is going to be a really important skill going forward, both finding local extrema and sketching the graphs of functions, because that, I think, is just, it's a very cool end result to a lot of what we do in calculus, is just being able to kind of put together all these pieces and say, okay, well, I can interpret the derivative, I can find the derivative, I can interpret it, and I can tell you what it means, and I can use it to recreate a sketch of the graph of this complex function, which I think is very, very cool. So if this video confused you, go ahead and watch the next one, because I'm going to do a very similar example in the next video.